Welcome back, students. Today we're going to talk about the intermediate value theorem, which is kind of a direct consequence of the idea of continuity. So, what does the intermediate value theorem state? If we have a continuous function, okay, so if we put down our pencil and we don't pick it up, if we have a continuous function, what does that guarantee us? Okay, so what do I mean by that? If we look at this graph here, I don't know what's happening from -2 to 4. But I want to know, are we guaranteed some point where the y value is 1? Are we guaranteed to go by 1 on the y-axis? And the idea is, if this is a continuous function, we have to pass by 1 at some point on the way from -2 to 4, because we're going to pass by every y value in this range. So I drew a potential graph in blue. Another potential graph would be something that looked like this, or maybe something that looked like this. You'll notice that the blue graph goes above the box, the green graph goes below, the pink graph goes back and forth in the middle, but we do go through every single value from -2 to 3. We have to go by those. So this is the intermediate value theorem. If f of x is continuous, we are guaranteed a value f of c is equal to something in our range. So if we know that -2 is at -2 and 4 is at 3, then we're guaranteed a value of 1. So let's look at a couple of examples. Does the intermediate value theorem guarantee that f of x equals x sine x plus 1 has a 0 in the interval 0 to 3 pi over 2? So the way in which we'll do this is by plugging in. So f of 0 is equal to 0 times sine of 0 plus 1. 0 times anything is 0, but sine of 0 is also 0. So 0 plus 1, so 1. Great. F of 3 pi over 2 then is 3 pi over 2 times sine of 3 pi over 2 plus 1. Okay, so sine of 3 pi over 2, hopefully you remember the unit circle, that is -1. 3 pi over 2 times -1 plus 1. And continue down here. 3 pi over 2 times -1. 3 pi over 2, well, we don't necessarily need that right now in this step, but it's just -3 pi over 2 plus 1. And -3 pi over 2 is bigger than pi, like it's further away from 0 than pi. And if pi is 3.14, this is maybe like -4.5, something like that. But it's certainly bigger than 1. So we do know this is negative. I don't even care exactly what it is. The fact that our first value was positive 1, and our value for 3 pi over 2 was negative, that means we have to cross through 0 because this function is continuous. So I'll draw that here just so you see it. 3 pi over 2, we said, maybe it's, I don't know, I guess it would be like 4.5, 4.6. So that would be maybe like here. That would be about where the point was. So we don't know exactly how these 2 points are connected, but we do know that they're connected continuously. So it could look like that. We know that it's going to cross 0. So we're guaranteed a 0 by the intermediate value theorem. Let's move on to our next question, which might be a little more difficult. We have a function f is continuous on -2 to 2, and some values of f are shown in the table. So we have x is -2, f of x is 3, so I'll graph that here. 0 gives us a value of b, which we don't know where that is yet. And 2 is equal to 4. Okay, f only has one 0 on the closed interval -2 to 2, and z, that 0 is not at 0. So that already tells me that this value of b is not going to be equal to 0, so I can go ahead and get rid of that. But all of our possible values of b. So if we look, we have -3, -2, -1, and 1. If we had a value at -3, then for this to be a continuous function, we would have to go from 3 to -3 somehow. It doesn't have to look like this, but it would have to pass through all of these y values. We would end up crossing the x-axis twice because in order to get below it and then back above it, we need to cross twice. The only time in which we can touch the x-axis once is if we just touch it and come back. So you'll see, -3 wouldn't work. If we looked at -2, same problem. We have to go below and then back up. Same thing with -1. However, with 1, it would actually work. Now this is strange because it looks like we could stay above 0 the whole time. But we are told that we do have a 0, and our graph could look like that, for example. It could also look like this. We don't know, but the only possibility out of these 5 that would work would be 1. Okay, let's look at our final example. The rate in calories per minute at which a person using an exercise machine burns calories is modeled by the function f, where t is in minutes and f of t is given in calories per minute. Selected values of f are given in the table. Is there a time t between 12 and 16 at which f of t equals 10? Okay, so if we looked here, yes, it looks good, right? We have 12 gives us 7 and 16 gives us 15. So we definitely would have to pass by 10. However, our answer is actually no here because we don't know if this is a continuous function. It doesn't say in the problem that this is definitely continuous. And for that reason, we cannot guarantee that we would have a value f of t equals 10 in that interval. Now, this is a person on an exercise machine, so it's very hard to imagine this being discontinuous. Like, it's hard to imagine there being some sort of asymptote or jump discontinuity. But we just don't know, so we can't guarantee it. No, since we don't know if f of t is continuous or not. We're not guaranteed a value. Okay, so this was a video on the intermediate value theorem. I hope you learned something, and I'll see you next time.